Hey, first hour's honors chem. Tomorrow we will be doing that lab where we're going to separate some sand, some salt, and some iron. Hopefully you have that all designed and your lab report is all ready to go. What I want you to do is go through this note pack. We went through two of the pages that talked about separation. I want to hit the other two pages. One of the pages looked like this. Consider the four containers below. When we took some notes when I was gone, one of the things they talked about was what an element, what a mixture, and what a compound is a little bit. And so let me see if we can talk through and get a better understanding. Which one of these are mixtures of A, B, and C? If I'm looking at these containers, I'm looking for things that have more than one type of thing. All of these have similar sort of things. That's not a mixture. But this one has a three-pronger, two, and a one. So B is definitely a mixture. These three are exactly the same, so that's not a mixture. But these ones have a mixture of different types of things. B and D are definitely mixtures. Pure substances are things that only have one kind of thing. So the ones that I ruled out, this one is pure, whatever it might be. It's all the same type of stuff. So is this one. So A and C are pure, which contain only compounds. A compound has to be a combination of more than one kind of thing. So when I'm looking, I'm seeing this one right here has a large size. I don't know what we should call it. I guess we're going to call it an atom tied to two smaller size. So that is two or more kinds of things. So that is definitely a compound. So this A has compounds. This says only compounds. B has a compound, two little things tied to a big thing. But this and this would be considered elements because they're only one kind of thing. So letter A does not have letter B does not have compounds. Letter C, this is a tricky one that we haven't really talked about too much. Since this and this are exactly the same size, we're going with this assumption that, well, they must be the same thing tied to each other. You've probably heard of O2. You've probably heard of H2. Maybe you've even heard of N2. Oxygen, hydrogen, nitrogen. All of these could represent one of those types of things. That is only an element, so C is an element. Finally, the next one, this D. This is a compound because it's a big thing tied to a small thing. It's two different kinds of things. This is the same compound. There's two of them in there. This is a different kind of compound, but D contains only compounds. So we didn't use letter B. Why? Because it doesn't contain only compounds or only elements. It had a mixture. Another way of drawing things, consider the four containers below. Which things are mixtures? Mixtures have to be two or more kinds of things. For instance, on letter C, there's these types of molecules, and they're mixed with these types of molecules. So C is definitely a mixture. Even though these are all clumped together, they are not arranged in a nice, neat, orderly fashion where we can tell that there's the right amount of them. It's like they were just all stirred together in a liquid. B is also a mixture. But pure substances are things that have only one kind of thing or only have compounds in them. We don't know a lot about it, but D is considered a pure substance. It's some sort of a crystalline structure or a solid structure, all of the same type of thing. It's going to be maybe a little confusing because there's different things, but the way the arrangement is very systematic. The dark next to the light, next to the dark, next to the light. It's almost, you've probably heard of table salt. Table salt is sodium chloride. So if we had a sodium next to a chlorine, next to a sodium, next to a chlorine, even though they're two types of elements, it's still considered a compound. And a compound is a pure substance. So letter A is a pure substance, which contain only compounds. Okay, compounds have to be two or more elements tied together. It's kind of new to us. Let's see. C. All of these are compounds. They're not the same, but they're not asking if they're mixtures or pure. They're just saying which has compounds. C has compounds. D, everything is exactly the same, so that's only an element. A, if we truly have a systematic lattice structure like this of something tied to something, and it's very systematic like this, it's also considered a compound, so that's going to be a compound. Now, what about letter B? Does it take, okay. So the way I see it, and it's tough because you can't blow up this enough, but all of these things are sort of touching but not chemically combined. You could misread this graph and you could interpret it differently, but I'm seeing is every one of these things is not attached to these. So all it is a bunch of elements and it's a mixture of them. I'm going to say that B is has elements, it's just a mixture of those elements. Next one, consider the four containers below. Which of these are mixtures? Mixtures have to have two or more kinds of things. So when I'm looking around is, well, these are all the same, so that's not a mixture. Every one of these has a big dark one tied to a little white one. That's not a mixture. There's only 3 of these and they're all exactly the same. That's not a mixture. And even these are all the exact same things. That's not a mixture. Which of these are mixtures? None of them are. They are all pure. All, or A, B, C, and D. So mixtures versus now compounds. Which ones are compounds? In order to be a compound, we have to have 2 or more different kinds of things tied together. Not a compound. This is going to be well, really what it is, it's a diatomic molecule. There are 7 diatomic molecules. I'm going to say the phrase, horses need oats for clear brown eyes. You'll hear that again later. We don't need to hear it all. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all the 7 things that are found. All of them are gases, and they're all found as, maybe bromine's not. Bromine is actually a liquid. Even iodine is a solid, so they're not all one type of phase. They are all diatomic, so any of these could represent any of those. These are all diatomic, which contain only compounds, not A. But B does, because it's a big tied to a little, big tied to a little. Every single one of those, B is a compound. A was all elements, so I'm going to put an A right there. Letter C also contains compounds. They're all the same compound. Letter C. Letter D has all elements because they're all the same type of thing, so D goes right there. Which of the containers in number 7 contain a gas, a liquid, a solid? It's hard to be definitive about this, but I think you'll remember when we drew particle diagrams of gases, if I put some whooshies in there, we'd probably realize, if they're all spread out and moving, A and C are definitely gases. I don't know if B is perfect. For instance, I would think B should take the shape of the container. So maybe if I had a container that looked more like that, I would declare B a liquid. So that one's a tough one, the way that the person, whoever decided to draw it, did it. Letter D is definitely a organized structure. It's a solid. So letter D contains solids. Flip to the page like this. This is one you didn't have to do much, but you were told, hey, somebody took a couple of different compounds of carbon and oxygen. We could guess as to some of these, what these formulas might be. You may have heard of some things about carbon and oxygen, like the stuff that carbonates your beverages, CO2 or something like that. This walked you through how to try to make best guesses you can't see at the particle level. So how did people come up with these ideas that we know exactly how many carbons are tying up to exactly how many oxygens? And it has to do with taking large samples and doing some tests and looking at large scale data. And so you see lots of things like if we took, 100 grams of compound A and we broke it apart, it would have 57 grams of this and 42.9 grams of this. But if we took a different compound also made of carbon and oxygen, we would have 72 grams of this and 27.3 grams of this. So what it says is let's look at the ratio of the masses of oxygen to carbon. And what we found out is A has a ratio of 1.33 to 1. We don't really need the 1, but 1.33 grams of oxygen for every 1 gram of carbon. How do I know it's oxygen on top? Because the mass of oxygen is over here. That's how we divided it. And the mass of carbon is down here. This one is 2.66 grams of oxygen to 1 gram of carbon. So in other words, compound B has twice as much oxygen for the same amount of carbon. So once we make this as this improper fraction, we can't have, okay, we don't know this, but let me just make this statement. Particles don't come in partial particles. When we have atoms, when we start learning about what those are, we don't have a third of an atom or a fourth of an atom. Atoms are going to be a integer or a whole number. And so if it's a 1.33 to 1, we need to figure out, we need to multiply, we need to change it into this. 4/3. 1.33 is like 1 1/3, which is 4/3. So it's 4 parts oxygen to 3 parts carbon. And really to say parts, I could say 4 grams of oxygen to 3 grams of carbon. But we got to think at the particle level. So, but the other one is 2.66 to 1, making that 2 2/3 into an improper fraction, and it's 8/3. It's 8 parts carbon. Whoops, I said that wrong. 8 parts oxygen to 3 parts carbon. So how would you draw this? Atoms of carbon and oxygen have the same mass. So how would you draw 4 oxygens and 3 carbons? Well, and this shows a diagram, and I wish I would have just done this, but I'm not going to stop the video and go with that. This shows the diagram of showing 4 oxygens and 3 carbons. This is, let's see, this is 4 oxygens and 3 carbons. So here's a atom, a molecule of C3O4. And here's another molecule of C3O4 versus compound B would have C3O8. So it would have 3 carbons for every 8 oxygens. Or maybe it isn't telling us how many carbons and oxygens. You see, that's only if carbon and oxygen had the same mass. If all atoms were the same size, the same mass, the only way we could get these ratios is to have 3 oxygens tied to 3 carbons tied to 4 oxygens, or 3 carbon down here, 3 carbons tied to 8 oxygens. But there's another way of looking at it. Somebody decided, well, maybe atoms of oxygen are heavier. I'm reading right here. Maybe atoms of oxygen are heavier than carbon atoms by the ratio in compound A. Maybe a oxygen, let's see which number was on top. That was the bigger number. Maybe an oxygen is 4/3 bigger than a carbon. And so maybe it's got a weight of 4 versus 3, but it's just 1 carbon tied to 1 oxygen. And on the next one, 8/3, well, about the only way, if we're saying that oxygens are bigger by a 4:3 ratio, to have an 8:3 ratio, we'd need 2 oxygens. We'd need 1 carbon and 2 oxygens, CO2. So people started asking, what makes more sense? That every atom is exactly the same size? We get things like C3O4 and C3O8, sounds complex and complicated. Or that some atoms are bigger than the other, and we get ratios like CO, also known as carbon monoxide, and other ratios like CO2, also known as carbon dioxide. Okay, so let me just try this fresh and see if this works out, because this is the one you guys had to do. You were supposed to make ratios, and it told you to do the ratio of the mass of copper to the mass of oxygen. So you had to put the copper on top of the oxygen. For the first one, 79.9 over 20.1, 79.9 divided by 20.1 gives us a, you know what, I'm going to just say about 4. I know you may have written down 3.98, but it's about a 4 to 1 ratio. 4 parts carbon to 1 part oxygen. What about compound B? 88.8 divided by 11.2. Uh-oh, got to do this. 88.8 divided by 11.2. I'm almost seeing the writing on the wall. It's still not working. I'm seeing that it's going to be about 8. Think I got it worked out. If we had 88.8 divided by 11.2, we're going to get a ratio of about 8 to 1. How does the mass, okay, so the ratio, how does the mass ratio for compound B compare to that in compound A? Well, B, again, once again, has twice as much copper compared to oxygen. Not necessarily twice, well, compared to oxygen, as A. So, the next thing, they're going to ask us, based on these ratios, hey, in here we don't really have to have an improper fraction, I don't think. Okay, so atoms of copper and oxygen have the same mass. That's a hypothesis. So if they have the same mass, they're the same size. But what I'm going to do is, well, I will make my copper equal, it's doing it again. So I will make my copper be a circle that looks like this, and I'll make my oxygen, I suppose since you guys don't have color, I'll make my oxygen equal a circle that also looks like this with an X in it. And so, what if all atoms of copper and oxygen have the same mass? So I would draw them the exact same size. But I need 4 times as much copper to oxygen. So I would have, for letter A, I'd have 1, 2, 3, 4 oxygens, I don't know, tied to one, whoops, that's 4 coppers tied to 1 oxygen. And on part B, I'd need 8 coppers. And maybe, I don't know, I'd put them like this, and who knows? It'd be hard to dream this up, and it would look something like that. But somebody else said, well, wait a minute. Maybe it doesn't tell us how many coppers and oxygens. Maybe coppers are 4 times bigger than oxygens, but so this 4 to 1, the mass is 4 to 1, the mass of copper. But what if copper is just 4 times bigger? What if copper looks like this, and oxygen just looks like a, 1/4 as big? So then maybe we could just have one of these, which has a weight of 4, tied to one of these, which has a weight of 1. Thereby it'd be a copper oxygen would be a formula, would be, or maybe it'd be oxygen copper. I'm leading ahead knowing that the metal will come first. So how do you account for this next one? That's 8, it's 8 to 1. Okay, it doesn't mean, so this theory said I have 8 coppers to 1 oxygen. This other theory says coppers are 4 times heavier. So if you have 8 times as much mass of copper as you do oxygen, you might just have 1 oxygen that weighs 1 tied to 2 coppers that weigh 4 each. That's an 8 to 1 ratio. That would be, let's see, my big one was copper. That would be C, was it copper? Cu, 2 of those, oxygen. So which hypothesis seems more reasonable? Do you think that everything's exactly the same size, and then why would they be different? And that we're going to have formulas like Cu4O and Cu8O? It's possible. Or do you think everything in life's a little simpler than that? Think different atoms are different sizes, like these types are 4 times bigger than those types, and that we have really simple ratios of things tying up. 1 copper tied to 1 oxygen. All right, which hypothesis seems more reasonable to you? I would say the simpler one. Basically in life, in science even, but in life, the simpler answer is usually the correct answer. What we're going to find out is atoms do have different sizes. Some atoms are heavier, some atoms are lighter, and when they do get together, they always pair up in a whole number ratio, and a lot of times it's a simple whole number ratio, like carbon dioxide, carbon monoxide, or copper oxide. You're going to try a few now.